Distribution of the sample mean, Module 4, Part 4. Our objectives are to describe the distribution of the sample mean, samples from normal population, and to describe the distributions of the sample mean, samples from a population that is not normal. Recall from earlier lessons that X bar is the symbol used to denote the mean of a sample. Also recall that samples are used to make predictions about populations because it is not usually feasible to collect data from the entire population. We noted earlier that different samples from the same population yield different statistics. We now turn our attention to the importance of those differences. Statistics, such as the sample mean, are random variables since their value varies from sample to sample. As such, they have a probability distribution associated with them. In this lesson, we focus on the shape, center, and spread of statistics, such as the sample mean. You are familiar with measures of shape, center, and spread of data from previous lessons. A goal of this lesson is to use the probabilities of the normal distribution we have been studying to determine if the results of our sample are expected results or not. The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. The sampling distribution of the sample mean, X bar, is the probability distribution of all possible values of the random variable X bar computed from a sample of size n from a population with a mean mu and a standard deviation sigma. Illustrating sampling distributions. Step 1. Obtain a simple random sample of size n. You may find it helpful to review our discussion of sampling in Module 1. Step 2. Compute the sample mean. You may find it helpful to review measures of central tendency in Module 2. Step 3. Assuming we are sampling from a finite population, repeat steps 1 and 2 until all the simple random samples of a specific size n have been obtained. Objective 1. Describe the distribution of the sample mean samples from normal population. Remember, the idea behind inferential statistics is to use a sample to answer questions about the whole population. We know the sample statistics will only give us an estimate of the population parameters, but usually we have to live with this because it is either impossible or impractical to collect data from the whole population. We also know that if each of us took a random sample from a population, it isn't very likely that any of us would get the exact same sample. Everyone's statistics, mean, median, mode, standard deviation, etc., would be a little bit different. It turns out if we looked at all the possible samples of a given size, say 5, from a population and graphed all of the means from those samples, they would form a normal curve. That is what we mean by the distribution of the sample mean. If these means from all the different samples form a normal distribution, then we can talk about the mean of those sample means, the median of those sample means, the standard deviation of those sample means, etc., because the means of all those samples are themselves a set of data. Here's an example with pennies. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 of a gram, 0.02. Approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n = 5 from this population. This is asking you to find the mean and the standard deviation of the means of the 200 samples. Actually, they found all the samples for you and calculated the means, which will be in a table 2 slides ahead. The data on the following slide represent the sample means for the 200 simple random samples of size 5. For example, the first sample of n = 5 had the following data. They picked out 5 pennies, and the weights were 2.493, 2.466, 2.473, 2.492, and 2.471. Then the mean was calculated, and recall we find a mean by adding up all the numbers and dividing by how many, in this case 5. So the mean for this one sample is 2.479. They did that for 199 other samples, and these are the means that they found. The mean of the 200 sample means in that table is 2.46, the same as the mean of the population. The standard deviation of the sample means is 0.0086, which is smaller than the standard deviation of the population, which was 0.02 grams. Technology was used on the 200 means in the table to get this number. The next slide shows the histogram of the sample means. Note the bell shape. What role does n, the sample size, play in the standard deviation of the distribution of the sample mean? In other words, what will happen if we take larger samples? Why does it matter? The larger the sample size, the more work and the higher the cost. We would like to use as small a sample size as possible. As the size of the sample gets larger, we do not expect as much spread in the sample means, since larger observations will offset smaller observations. Now we want to use that same penny data, except we want 200 random samples of size 20 from the population of weights of pennies. And remember, the population mean is 2.46 and the population standard deviation is 0.02 grams. So here's a histogram that represents the means of those 200 samples. The mean of the 200 samples for n equal 20 is still 2.46, but the standard deviation is now 0.0045. And remember, it was 0.0086 when we had a sample size of 5. As expected, there is less variability in the distribution of the sample mean with a sample size of 20 than with a sample size of 5. Suppose that a simple random sample of size n is drawn from a large population with mean mu and standard deviation sigma. The sampling distribution of x bar will have a mean, which is represented by mu sub x bar, equal to the population mean, and a standard deviation with the symbol sigma sub x bar equal to the population standard deviation divided by the square root of the sample size. The standard deviation of the sampling distribution x bar is called the standard error of the mean and is denoted with the sigma sub x bar. This is a measure of the accuracy with which the sample represents the population. So accuracy is going to be better with larger sample sizes, so you'll have to decide when you do a study how accurate is accurate enough when you decide what sample size you need to use. We need to know the mean and standard deviation of the sample means in order to calculate z-scores and hence probabilities or likelihoods that something is possible. If a random variable x is normally distributed, the distribution of the sample mean x bar is normally distributed. We need to know normality so we can use z-scores and areas to calculate the probability. The weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02 of a gram. What is the probability that in a simple random sample of 10 pennies minted after 1982 we obtain a sample mean of at least 2.465 grams? So how likely is it if we draw a sample of 10 pennies that the mean is going to be at least 2.465 grams? So the sample mean is normally distributed with a mean the same as a population mean, so that's 2.46, and then we calculate the standard deviation by using the population standard deviation divided by the square root of 10 to get 0.0063. And we need that in our z-score formula, which you will recall. The value we're interested in, 2.465 minus the mean divided by the standard deviation, is equal to 0.79. So then we can use the normal distribution to calculate the probability, which is the same as the area under the curve to the right of 0.79 because we want scores greater than 0.79. Using the same website we've been using, that's calculated to be 0.2148, which could be turned into a percent to say that there's a 21% likelihood of this happening. If you're using a TI-84, here are your instructions. This video has been broken into 2 parts. Now continue on with Module 4, Part 4, Video 2.